Alright, real-life applications of trig. As the Earth goes around in circles, the moon's gravity causes the oceans to bulge out at the equator, and that causes the ocean water to get deeper and shallower as the Earth revolves, in a pattern that we can predict using a trig function. And in this example, they say you're at a harbor, and the depth of the water is going up and down like a cosine function as time goes on. Now, they have not given this to us in a very nice form. Cosines are supposed to look like y equals a cosine b x minus c plus d. So let's get that fixed up first. Our depth should be 5 cosine 0.5. Technically, there should be another bracket here because we have a horizontal phase shift of 0, and then we have our plus 12 on the tail end. So that's how a cosine is really supposed to look. You might find that helpful when we're picking this thing apart. Now, determine the maximum and minimum depths of water in the harbor. They've said that the midline for the water is 12. That's our average depth. That's the mean sea level here. And then our amplitude is 5, which means the water gets 5 meters deeper than 12, 17 meters. And at its minimum, the water is 5 meters shallower than that, so 12 minus 5 is just 7 meters. The water in this harbor goes from 17 meters deep down to only 7 meters deep. For the period for any sine or cosine is 2 pi divided by b. In this case, that's 2 pi divided by 0.5, which is 4 pi, which is about 12.56 hours. It normally takes about 12 hours because that's how long it takes for you to go from one side of the Earth where you're facing the moon to the opposite side of the Earth where you're totally away from the moon. That's typically a tide cycle. Write a suitable window which can be used to display the graph of the function. If you're graphing this on your calculator, well, the period is 12.56 hours, so at the very least you want your x minimum to be 0 and your x max to be 12.56. Let's say that's your smallest reasonable window. You could make a case for going 0 up to 24 hours as well if you wanted to see what happens in an entire day, but I'd say 12.56 is your bare minimum. Vertically, I urge you to not go 7 to 17. It is best, whenever possible, for your graphs to start out at 0 on the vertical axis. And you don't want to stop exactly at 17 either, because then the calculator draws your wave right up to the very top of the screen. And then if you start doing traces or any kind of calculations, it starts putting text up here and writes right over your graph. So don't stop at 17. Even 20 might not be quite as much space. Give yourself some room and go to like 25 or even 30 so that the graph is visible, but it's not taking over the entire window and crammed in real tight. Now, in D, they start getting us playing around with this equation they've given us. What is the depth of the water at 2 o'clock in the morning? They said T is the number of hours after midnight, so 2 a.m. really is T equals 2. And at that point, the water depth is 5 cosine 0.5 times T plus 12, which is 5 cosine 0.5 times 2 is just 1 plus 12. Now, remember when we said 2 pi up here? As soon as we did this, we committed to working in radians. If you want to work in degrees, you should have said 360 over 0.5 for this spot. But typically we just work in radians. That's the tradition in advanced math. So make sure you're in radian mode before you do the cosine of 1. That's 0.54. Multiply the result by 5, add 12, and I get a water depth of 14.7 meters. Now, a ship which requires a minimum of 8.5 meters of water is in harbor at midnight. By what time must it leave to prevent grounding? Meaning there isn't enough water under it to keep it afloat and the keel actually runs into the seabed. And this is actually part of the same question. When is the next time that the ship can return to harbor? So, excuse me for a moment. I'm just going to rub out part F, and there we are. Okay, now we can solve both of these at once. The idea is the depth of the water starts out at 17, and it's going to drop to 7 meters, and then by 12.56 hours later it will have come back up. 8.5 meters is a big deal for this boat because it's when the boat runs out of space. And there's a horrible grinding noise as it settles onto the seabed and probably takes lots and lots of damage. So right here is a deadline by which the ship has to get out of this harbor to avoid running aground. And then all through here the water is too shallow, still too shallow, still too shallow. And over here is another point in time where the water is rising again and the ship can come back. So if this ship had business in harbor, it would have to duck out by this time in the morning, wait, and then come back by this time here. Question E asks about the first time, when does it have to leave? And question F asks about the second time, when is it able to return? So let's see if we can figure out both of those. The depth, we said before, is 5 cosine 0.5 times t plus 12, and we want to know when does that equal 8.5. Subtract 12 from each side. 5 equals cosine 0.5 t. Oops, I'm sorry, I didn't mean to put a 5 there. Let's take that back. Or I didn't mean to put an equals there, rather. We have 5 cosine 0.5 t equals negative 3.5. That's after I subtract 12 from each side. Now we divide by 5, and we get cosine 0.5 t equals negative 0.7. Now, forget about the 0.5 t for a moment. Suppose you just had cosine theta equals minus 0.7. You remember how we would solve those? You draw axes. You say, okay, cosine is supposed to be negative, which means I must be in one of the two quadrants where cosine can produce negative values, there or there. And then we go to the calculator, and we don't tell it about the negative sign. We just give it 0.7, make sure you're in radian mode, and do inverse cosine, and it gives us a reference angle. It tells us the reference angle is basically 0.80. Either in this direction, or it could be in this direction as well. Either of those are valid reference angles. Now, we don't want to work with reference angles. We need standard angles that actually mean something to us. So the standard angles for these two are either pi minus 0.8, which is 3.14 minus 0.8 is 2.34. Or the other option is pi and then keep going another 0.8. So pi plus 0.8, which is 3.94. Those are our two valid angles if this were just cosine theta. Take a minute, make sure you're good with that. We did this a couple sections ago, and now it's back helping us with our word problems. Okay, if you're all right with these angles, that's what we would do if this was just theta. But wait, the angle isn't just theta, it's 0.5t. So instead of saying theta equals 2.34 or theta equals 394, instead we're going to say where theta used to be, we actually have 0.5t is 2.34, or 0.5t is 394. So to finish solving these, we divide them both by 0.5, and we get either t is 468 or t is 788. Those are times, and they're in hours. If we want times to the nearest hour and minute, we have to do a little bit of tweaking to make these behave for us. So I'm just going to get rid of this diagram. Shoot. Okay, that didn't work exactly the way I wanted, but we'll just ignore this and hop over it. If the time is 4.68 hours, that means 4 o'clock in the morning plus 0.68 of another hour, which we do as 4 o'clock in the morning plus 0.68 times 60 minutes. 0.68 times 60 minutes is 40.8 minutes, so I'm just going to call it 41 minutes. The must-leave time is 4:41 a.m. For this next time, 7.88, that means 7 o'clock in the morning plus 0.8 of an hour, which means 7 plus 0.88 times 60. 0.88 times 60 gives me 52.8, basically 53 minutes. So our ship must bug out by 4:41 in the morning, and it will be safe to return starting at 7:53 in the morning.